In this video, we're going to look at rates of change of functions over particular intervals. To introduce this idea, let's think of a real simple situation of driving a certain distance in a certain amount of time. So in this graph here, what you see is this kind of zigzag set of lines here represents the idea that we have this vehicle traveling over time, and it's not necessarily going the same speed the entire time. So you can see on the x-axis I have time in hours, on the y-axis I have distance in miles. And so the idea here is I can see I haven't gained tons of distance over this set of time here, but then over this next period of time in the next segment I've gained a lot more distance during that time. So we have different things happening in different segments of this time period that we're traveling, but we can still talk about overall how fast are things happening, and that's kind of represented by this dashed line here. So this dashed line kind of goes from here, 0, 0, right, to, I'll just go ahead and label it, the point 0, 0, up to this point here, which we can see is the point 2, 100. And that's really representing this idea that I've covered 100 miles in the 2 hours that I've been traveling. And so pretty quickly you would realize, okay, well, 100 miles in 2 hours means I'm going on average 50 miles per hour, right? And I know that that doesn't mean I'm going 50 miles per hour for the entire trip, but that's what I've averaged. All right. Now let's just take this little computation we did and let's just write it a little bit differently. One other way to think this through would be to say, here I was at 100 miles. At this starting point, I was at 0 miles. And so I'm going to figure out, okay, well, what's the difference between where I was at here and where I was at here in terms of the distance? And then I also, on the bottom, can do the same thing, right? Here I was at 2 hours of time. I started out at 0 hours of time. And of course, that gets me the exact same computation. But the reason that I introduced this is because this is really what we're doing when we're looking for rates of change. We're looking at how one quantity, in this case the distance, is changing as the other quantity, in this case time, is changing as well. This is what we refer to as our average rate of change. All right. So on the next page here we have our formal definition, but this should look familiar. So we learned in our function notation, right, that f of b and f of a are just the y values of the function at x equals b and x equals a. So this is taking the difference in y values, just like I did on the previous page, and dividing it by the difference in x values. Or to put it in words, it's the change in the y over the change in the x. Okay, and so on this picture here, you can see, right, this is the point, right? The point x equals b, y equals f of b, and this is the point here, x equals a, and y equals f of a. And so we're just plugging those directly into this formula anytime we want the average rate of change. And it tells me, as I travel from this x value to this x value, on average what's happening. Okay, I can see that what at first I dip and then I climb a whole bunch. But on average, it's telling me in this particular picture that I have a positive rate of change. In other words, I've gained in height as I've gone to the right in my x value. All right, so let's take a look at this in a formulaic sort of way. So this one gives us a function, f of x is equal to 3x squared plus 1. And we want the average rate of change between x equals -1 and x equals 2. All right. So from that previous definition, we know if we want to find this average rate of change, we're just saying, okay, let's take f of 2 minus f of negative 1 divided by 2 minus negative 1. And of course I could have put the f of negative 1 first up here on top and f of 2 second, as long as on bottom I did the same thing, put the negative 1 here and the 2 there. All right, but this is just fine the way we have it set up. So what is f of 2? Well, f of 2 is plugging in x equals 2 into 3x squared plus 1. So there's my f of 2. Anytime you have multiple terms that you're looking at, you should definitely put parentheses around those terms when you're subtracting them from something else. So that becomes really important with that subtraction. And then, of course, 2 minus negative 1 we understand is just the same as 2 plus 1. So here, 2 squared is 4, times 3 is 12, plus 1 is 13. So we have 13 minus negative 1 squared is positive 1, times 3 plus 1 is 4. Divided by 3, so that's of course 9 over 3, which is positive 3. Okay. There's our answer right there, but let's also understand that when we want to think of this as a ratio, that's 3 over 1. So what that really means is I'm gaining 3 ticks in height for every 1 tick I go over horizontally to the right. And I think it's worth just not losing track of the picture of what's going on here. So in our graphing calculator, if we pull that out and we go to our y equals menu, we can go in and type in 3x squared, and so I'll just find this little variable button here, hit x, and then my square button, plus 1. And what I want to do is take a look at what this function looks like over the interval we're interested in, right? Which was x equals negative 1, and you can't see it right now, but x equals 2. So if I hit graph, first of all, it'll show me the graph, and here's x equals negative 1, here's x equals 2, but there's a lot of space out here we're not using. So it might not be a bad idea to go to Window and just adjust the x values we're looking at. So maybe we only look at I don't know, how about negative 4 to 4, for example, because we want to focus in on that smaller window, and just to make sure we're not cutting off too many y values. I don't really need these negatives, so I could start my minimum y value at 0, and I could go up. Let's just go up to 25. See what that looks like. So here's a picture, and so what are we saying when we're saying the average rate of change is 3? What we're saying is that on average, as I travel between x equals negative 1 and x equals 2, for every 1 unit I go to the right, I go up 3. Or perhaps another way we could look at it is looking back at this unsimplified version, 9 over 3. This is saying as I move 3 to the right, I'm going to go up 9. And so let's see if that bears out here. Okay. One little nice feature on a graphing calculator is to use the trace function. That allows you to put in any x value and it'll tell you what the y value is. So if I hit trace here and I start at negative 1, right, there I am at y is equal to 4. Okay. If I then go over 3, right, over 3 takes me to x equals 2. So I'm going to go ahead and then type in trace again, x equals 2. And that took me up to 13. And so, of course, it told me I was at 4 before. Now I'm at 13. And so you notice those are the numbers I had right here. So all this information here is literally telling me on average what's happening. How is the function changing as I move to the right? So let's take a look at one other example where we have a formula in front of us. So it says find the average rate of change of g of x on the interval 4, 7. So we know the drill by now. Our average rate of change is going to be the difference between g of 7 and g of 4, all divided by 7 minus 4. Okay, but then g of 7, what is that? That's 3 divided by a 7 plugged in for x. And then we have 3 divided by a 4 plugged in for x, so 4 minus 2, all divided by 3. So this is going to be 3/5 minus 3/2, all divided by 3. And you can use multiple strategies here in order to solve this complex fraction. I'm just going to go ahead and combine the fractions on top here, which of course I know requires me to get a common denominator. So the least common denominator of 3/5 and 3/2 would definitely be 10. So I will multiply by 2 on top and bottom here to make 10 on the bottom, and by 5 on top and bottom here. So this is going to be 6/10 minus 15/10, all divided by 3. Now 6/10 minus 15/10, that's going to give me negative 9/10 divided by 3. But now we know when we're taking fractions divided by numbers or other fractions, the idea is dividing by a number is the same as multiplying by its reciprocal, right, or its flip. So let's go ahead and artificially make our 3 into a fraction, which we can do by just sticking a 1 on bottom. So this means this is the same as negative 9/10 times the reciprocal of 3 over 1, which is 1 over 3. And then I can do a little bit of canceling out there. So this gives me negative 3/10. All right, and just really quickly, let's go ahead and look at the graph to make sure that this is all making sense to us. So here's our graph. We'll go back to our y equals menu. We can just have y1 selected here and hit clear. That gets rid of our old graph. And then we'll type in 3 divided by x minus 2. Now in our calculator we do have to be careful. When I hit this division, it's going to divide by whatever comes next. So I don't want to just put an x here because it'll only divide by x. What I want to do is divide by x minus 2, that entire thing. So in order to make sure our calculator does that, we go ahead and put parentheses around the x minus 2. Okay. Now we're on the interval 4 to 7. So let's go ahead and just go to our window and adjust that immediately. So maybe we go from a minimum x of 3 to a maximum of 8. And then I'm guessing that these y values aren't going to be pertinent anymore. Right now we're going from 0 to 25 from our last example. And if you take a look here, the bigger the x gets, the smaller this whole thing should get, right? Because we're going to be taking 3 divided by a number. So it's just going to get smaller and smaller. So I don't think I need very large numbers here. So perhaps what we'll do is just go from y equals 0 to y equals 2. And that probably should be good enough. All right, so there's our function. Remember, we started it at x equals 3. We ended it at x equals 8. So that means x equals 4 is right here. X equals 7 is right here. So from this point to this point, we're saying we're averaging a drop, because of this negative, of 3/10 for every 1 unit we go to the right. So does that make sense? Drop 3/10 as I go 1 to the right, drop another 3/10 as I go 1 to the right, drop another 3/10 as I go 1 to the right. That seems like what the average rate of change actually is. So just wanted to bring it back to that picture each time we do one of these formulas. Now in this last example, we don't have a formula to look at, but we do have a data table. So it says the Mauna Loa Observatory, located in Hawaii, has been monitoring carbon dioxide levels in the atmosphere since 1958. The table lists the average annual CO2 levels measured in parts per million from 1984 to 2006. So part A asks us, what is the average rate of change in CO2 level between 1984 and 1994? Now, I guess the question mainly here is that since we know that the average rate of change is the change in y over the change in x, the only question is, okay, what's y and what's x? Is the CO2 level y or is that x? So there's a couple ways to know. Number one, anytime you have a time variable, that always tends to be the x, because that's what we would refer to as the independent variable. Okay, so time is in most cases going to be the x value in most cases. But a more sure way of really understanding this is if we just tick back real quick to the last example. It asks us find the average rate of change of the function g of x on the interval 4, 7, right? Now we know that these are x values that they're referring to, and when we're talking about function values, right, g of x is a y value. So if we pay attention to the way they're asking this, they're saying, what is the average rate of change in CO2 level between 1984 and 1994? Well, and that means this has got to be y, right? Because they're asking us for the average rate of change in that, and then this is x. And so we definitely want to have the CO2 level as our y value, as our dependent variable, and then of course the years is the independent variable. All right, so 1984 and 1994. So here's our 84, here's our 94. So this literally is just me saying, let's take the 94 level minus the 84 level, and then take 1994 minus 1984, which is just, of course, 10. So what we get there is 1.46, and then we got to make sure our labels are correct here, right? So what is CO2 level measured in? Well, it's measured in parts per million, right? So parts per million is the y unit, but the x also has a unit associated with it, right? It's years, okay? So 1.46 parts per million per year. And we can answer the same thing here. Part B, what is the average rate of change in CO2 level between 1996? So that would be this one, and 2006. And so again, we're just taking this difference, 380.9 minus 362.7. (2006) minus 1996. And so our answer here is 1.82 parts per million per year. All right, so let's kind of step back here. It's saying up here we're saying that the CO2 level is increasing by 1.46 parts per million per year on average, right? It's not saying it's doing that exactly every year, but on average that's what it's doing. But then we go 1996 to 2006, and when we take those as the 2 points we look at, we see an average rate of change of 1.82 parts per million per year. So what we have is that the average rate of change is a lot greater during this time period than the previous one that we had looked at.